Let's begin implementation of infinite queue. This is lab05. So let me begin with the empty folder for that in another terminal. Let me change directory. I have another directory there. So begin with the testing code. So let's use iostream main function. So we are going to define iqueue class, infinite implementation of a queue. So this class will provide all those functionalities. Suppose it is there, then we can test it. So here is a queue variable there. Infinite queue, there is no capacity limit, so we do not provide array capacity. It's not array based one. Then at the very beginning, queue should be empty. Also, the length of the queue should be 0. As I push data there, then queue is no longer empty. Then length of the queue should be 1. For compatibility with some other implementation, we will give a full function as well, but that will never be full because it's infinite capacity implementation. So let's begin with a very simple implementation of those few functions. Like in infinite implementation of a stack, we are going to use a node class. Then at each .h file of the class, we used to do if not defined file name, define file name, and if purpose of this one is that in a huge project, if node.h is included in several places, you cannot have a same declaration of class multiple times. So these three lines just avoid or eliminates the multiple inclusion. Once it's included, the second inclusion is automatically avoided. But now we have a more convenient way of doing so. This if not def define and if it's a most classical way of doing so now. Pragma once is just one single line is equivalent to those three lines. So pragma once may be more convenient. So node class like the one used in infinite implementation of stack, we need a data portion and we need a link to another node in public interface. We provide the data directly to the constructor and then that will be initialized into data member and then link will be null at the very initially it's created. So in node.cpp implementation, we include the interface part and then we implement a constructor. So data member will be initialized with the data provided at the constructor and then link member should be null pointer. That's what we need to do at the constructor as initialization. And null pointer is defined in iostream. So we include the iostream there. So node structure is created. Now we are ready to create queue class. So pragma once class queue In private member, we are going to have a count variable which holds the number of data stored in the queue. And then we are going to have two pointers. One pointer is front of the node in the queue. Another pointer is a back node in the queue. Then in constructor, we are going to initialize those values. So member function, empty function does not change any member variables, so it could be const function. Full, same as a const function. And then length of the queue, it's also const functions. It simply returns the number of items in the queue, which is count. Then we are going to implement a push function, and then integer data is there. So let's now implement a queue class with the queue interface defined there. So in constructor, counter should be initialized to 0. And then pointer to the front node, null ptr, not assigned yet. The pointer to the back node, null ptr, will be the value. Null ptr is defined in IOStream library. Next, empty function is relatively simple because we have a count variable. If count is 0, it's empty. Full function, this is infinite queue implementation, so it will be always a false. And then length function, we can simply return the value in the count. So those are implementation of those some basic ones. Now we are ready to implement a push function. Data is provided. Then let's draw a picture to understand. Let's visualize this one. So when queue variable is created initially, it will have a pointer to the front node and the pointer to the back node. So here, if there is no node at the beginning at all, the front pointer is null, and then back pointer is null as well. So if this is the first time to enter, currently queue is empty, there's nothing, then front as well as the back. So as we add a new node, this the only node is a front as well as a back. So there's no other link there. So that will be done. So the very first time when queue is empty, we will have this kind of picture. But if there is some node existing, so here's a queue variable, front pointer, back pointer is there. Suppose we have already some node inside in the queue. So this is a front node. We have data. Then this front node is pointing to the next node. So we have another data. Now this is the back of the node. So here's a pointer to the back node is there. Suppose if we have some data already in the queue, then push means as we create a new node, as we wrap data by there, then push operation is the currently the last node, the back node, the link should be updated to point to the new node. And then the pointer of the back node should be updated to point the the node just added. Of course, when new node is created, the link is always null. So we need to do two things. This one, establish the link from the existing last node to the new one for push, and then the pointer of the back node should be updated accordingly. Those two things should be done. So we have two cases. The first, when queue is currently empty, and then if queue is not empty. So we figure out the two cases existing. Then at this moment, you may wonder, well, how do we know that those two cases actually cover all possible cases? Is that comprehensive coverage? Actually, to figure that out, we can visualize this way. So here, how do we find all possible cases when you deal with like a push function and so on? Then just imagine this way. So push means we have a queue variable, we have two pointers, and then nodes are added there. Then push means we add a new node always at the very end. So we are going to add there. Then just consider when you add a new node, push onto the queue, what will be on the left hand side of the new node, what will be on the right hand side of the new node. Just figure out all possible such cases. Then we can figure out what would be the comprehensive case coverage. On the right hand side of the new node, there's always nothing. There's nothing onto the right of the new node because that will be the back of the queue. But on the left, depending on current situation, so if there is no nodes in the queue at all, it's empty, all empty, then left hand side of new node will be the queue variable itself. But if nodes are already in the queue, then left of the new node will be existing node. So we don't see any other possibility in the visualization of the queue. So right hand side of the new node, always nothing. Left hand side is either queue or existing node. So when do you have a queue on the left hand side? When queue is empty, currently empty, left hand side of the new node will be queue. If it's not empty, then left hand side of the queue will be existing node. So based on that, we can write the code for that. So that's what we figured out by these pictures. But when you implement the push function, so consider those ones. So if queue is empty, then this is one case, else that's a second case. So here, as we do push always, we create a new node with data. So data is wrapped up by new node. Then if currently queue is empty, that's the picture of this one, then the new node should be pointed by front pointer as well as a back pointer. So new node is a front as well as a back. That's empty case. But if it's not empty case, this is another picture down here. So we need to do two things. First, the last node is here. Currently, last node is pointed by p back. So p back, the link member should be set to the new node just created. So we can establish this number one link. So currently p back link member should be assigned to the new node address. So number one link is established. Then p back should be now new node just created. So p back should be updated. So this is a number two link from this picture. When all the pushes are done, we just increment the counter. So that's the push implementation. So let's compile the program. So we didn't create the maker file yet. So let me clean the pictures. Then let's create make a file. So we have node.cpp, iqueue.cpp, main.cpp, so three CPP files. But ultimate goal is a.out. So main.o is needed, node.o is needed, iqueue.o is needed. Once they are available, we can put together by this command. Node.o is by compiling node.cpp, but node.cpp is dependent upon node.h. So compile only node.cpp. And then q.o, we need iqueue.cpp for translation, which depends upon iqueue.h. And then iqueue class also needs a node definition. So compile only b. And then main.o, we need the main.cpp, which uses a q class definition. Main.cpp is compiled. So that's a make file. So let me double check q definition where node is used. So we need to include the node definition, interface definition of a node. So all those dependency information is in Makefile. Now let's compile it. Here in q.cpp, the node class link member is accessed. And the same thing happened in stack implementation. And the link member is a private member of the node. So Q class cannot have access to that. One of the solution is a friend declaration. So in node class declaration, we declare iqueue class is a friend, which means that now iqueue class can have access to the private members. So compile again, run it. So far, the very few test case is passed. So we implemented the push, empty, length, and full. But at this moment, we cannot test the push function yet. So we'll do that on next video.